All right, we'll get started talking about post-quantum cryptography and how we've got dragged into this recently and what I know a little bit about it. So thanks for coming. I think just as a brief introduction to this problem, the window for proactive mitigation of basically crypto anti-agile patterns is right now. I've been brought to this problem of identifying these patterns in source code by especially our banking or financial services customers. I run a company called Modern, which does large-scale software refactoring and impact analysis. And this is becoming a key concern for especially the banking sector right now, feeling like should a sufficiently powerful quantum chip arrive, that they've got hundreds of millions or billions of lines of code under management. How are they going to go through all of that code and find these patterns, these hard-coded algorithms and secrets and key pairs and so forth that are that would need to change or that would effectively lead to broken encryption should such a thing arrive? If, as an executive, an engineering executive at one of these organizations, you still feel like that sufficiently powerful quantum chip is still 10 or 15 years out, it feels like the window to try to mitigate starts now, because they've had a long experience with how difficult it is to systematically go through their code and make any kind of change, right? After all, when working with a lot of these organizations right now, we're still dealing with end-of-life versions of WebSphere and obviously COBOL mainframe type code. Not exactly the tech stacks they want to be on. It just takes that long for them to make sufficient change in their code. So what I found is that we have a number of our banking partners actually working on this problem really uniquely and a bit in secret. They have researchers, many of them looking for these anti-agile patterns in code, identifying them and looking for technologies to basically itemize them and eventually replace them in their code. These things span from things like hard-coded keys and certificates to provider names and key links, and these are the kind of simple patterns. We'll see some more complicated ones here in a little bit. I've found, unfortunately, that many of our financial services partners are actually working on this problem alone. They've staffed their own research teams and are trying to identify these patterns. Luckily now there's a umbrella, there's kind of an interesting collaboration model that's forming inside of Finos, which is a financial services open source consortium underneath the Linux Foundation, where we're standing up a private repository of these patterns and in the form of open rewrite recipes, which I'll show in a little bit here, where these banking partners and members of Finos can all contribute their research and recipes to that essentially Apache licensed repository inside of Finos, and yet it's still private. Because their fear, of course, is that these patterns themselves are a map or basically a treasure map to the problems inside those organizations. It's the first time I've seen something like that, a collaboration model that has an Apache license to it, but is itself not publicly available. And it just kind of goes to describe the problem and how worried they are about this particular problem. I've been working on just a few characteristics about the capabilities we need if we're going to search for these patterns in code itself. And of course, these are probably not new to a lot of folks working in AppSec here. If I'm going to look for like a hard-coded, some sort of literal that is crypto anti-agile, it could appear in the context of a particular call like this SSL context.get instance where I don't even need a data flow capability to find it. It's almost, I could do this with a regular expression or a really simple AST-based search. Of course, the step above that is I have to be able to follow the flow of some sort of literal through a block or basically intra-block data flow analysis. That field or that like literal that I'm tracking could be defined elsewhere in the same file. So this is kind of the intra-file data flow or taint analysis capability. Many times these things flow across files in the same repository. And of course, if we're going to really comprehensively look at these problems across a large code base, we really do need to be able to build a technology that can find flow across files in different repositories inside the same, inside a particular customer as well. So we'll kind of go through how we're doing each of these phases, getting up to kind of a stage 5 flow across different repositories in the same organization. The first problem, even if I'm going to do this first step here where no data flow is required and I'm looking for something like security.getInstance where I've got this hard-coded TLS, if I'm just operating on the text of code or the abstract syntax tree, this is already a pretty hard problem because a method name like this getInstance is very generic. It actually, comes from the old Gang of Four pattern book on how to define singleton objects. So this method name is going to show up everywhere. And if I just try to do a textual search or an abstract syntax tree-based search, I'm going to find a ton of false positives. I did a quick search actually for every occurrence of just a method named getInstance and then tried to organize them by the receiver type. In other words, the actual type that method was defined on in just about 1,000 open source repositories and identified 998 distinct receiver types that have a method called getInstance on them. So it just kind of goes to show how it appears simple, to do a kind of textual search or AST search here, but this can kind of get out of hand really, really quick. It's really for all these reasons that really I was brought to this problem. I founded a technology about 10 years ago at Netflix called Open Rewrite. And Open Rewrite is it was really designed for large-scale refactoring. We later moved into impact analysis, but Open Rewrite's core data model is not the text of the code or the abstract syntax tree, but rather something we call the lossless semantic tree. So the lossless semantic tree contains type attribution information. It contains other metadata in the form of markers. In other words, when I look at this method called P right here, type attribution information that hangs on that abstract syntax tree node would basically would say what is the receiver type. It's actually a bit deeper than that. If I have a particular receiver type, what are its superclasses or super interfaces? What are all their other methods? What are their generic types? What are their arguments? What are their super interfaces? So if I'm just looking at a particular method call here called P, I could actually be in this directed acyclic graph, this really dense information representation called a lossless semantic tree. I could be looking at 2 or 3 million nodes or vertices hanging off of that one method invocation. This is really, unfortunately, the information that's necessary to find these accurately. If I go back to that getInstance example here, by having that type attribution hung on this syntax element, method invocation getInstance, I would be able to identify whether this getInstance was actually from, the security package, the receiver type I was really actually looking for. I would like to just show a few examples of what we call recipes, which are programs that basically extract information out of this LST and for search results or to make changes, just to give you kind of a broad sense of how we use the data in type attribution. And then I think the rest of this will make a little bit more sense. So I'm going to flip over for a moment and just look at a mark, but there's about 5,000 recipes available to me, but I'm going to do just kind of like a find deprecated methods kind of search, which is an interesting problem. I'm gonna look at about 200 repositories of code here roughly, and recipes are just programs. They can have options associated with them. I'm going to look for deprecated usages of Spring, popular Java framework, in the Spring code base itself. And so you'll see here the method pattern is I'm looking for anything that's org.spring framework, any subtype of that, any method name, any number of arguments. I don't really care. I just want to find Spring type methods that are in the Spring code base itself. And so if I run this, we'll start seeing the recipe produce these what we call search result markers on that LST, and this gets materialized back out to the text of the code to show a particular occurrence of this thing. So we see here that builder.connect TCP, this connect TCP method was deprecated at the time that this code compiled here. There's nothing about the syntax of this call that indicates to me that it's deprecated, right? To find that kind of information, I would have to look at the definition of this method and then look at what was annotated on that method. Or perhaps connect TCP is coming from a concrete class who in turn inherits from some interface, which inherits from some other interface, and the deprecation is actually indicated 2 or 3 levels up on the original definition of this method. And so this recipe that looks for fine method usages is really looking at that type attribution information to try to determine whether this thing is deprecated at that time. Recipes can make changes to individual places like this. They can also emit what we call data tables, and data tables are just rows and columns of information according to a schema of the recipe's choosing. So in this case, this recipe on find usages of deprecated methods decided to emit a data table called method calls. And method calls is just going to contain a row for every deprecated method that I found somewhere in one of these files. And this recipe thinks, well, I would also like to put on this information about what the actual receiver type was. So if I look at this, any individual row, this is the repository, this is the file that had a deprecated use. This was the actual code of that deprecation. This was the type that it was defined on, the name, the argument types, and so forth. So just like we normally do in Excel, I could basically take these 3 columns right here in pivot table and tell you what the most common usages of deprecated methods are in this business unit, in this 200 repositories. The shape of data, the type of data that we emit from a recipe is arbitrary. So if I look at the actual definition of this data table in code, it's really just going to be a value object. Like this is a data table defined in the recipe. This is any given row is going to have a source file, the method, the class name, the method name, the argument types. And a recipe is just a program going through this lossless semantic tree data structure. And every time I encounter one of these things, I just create another one of these rows. It's that ability to change this really dense lossless semantic tree directed kind of cyclic graph into a tabular data that allows us to build compositionally like higher and higher order units of analysis ultimately. This LST you saw, I was just running on a Java code base, right? So this the LST for Java itself is defined in something that's called a J. It's just a top level interface, and there's all these different type of syntactic constructs underneath it. The Java language consists of identifiers and method invocations, the typical static analysis stuff, right? As we went to build out other languages, as we went to build out JavaScript and TypeScript and Python and C#, et cetera, I initially believed that JS or TS, whatever we were going to call this top-level interface, was going to be just a completely unique set of LST elements. And as we really started mapping it out, there was a surprising amount of overlap between the data that was actually in a JavaScript or TypeScript LST and a Java LST. And I think the main realization here is this, that these C family languages actually share quite a bit more structure than it appears in the text of their code. they are printed in text very differently, right? Like the actual syntax to indicate a method is different, but the actual fundamental data on them is very similar. They have arguments, they have a receiver type, they have these sort of things. So as we went to build out the LST for JavaScript, and this is a bit controversial, we find JS, the base LST, extends from J, actually. And we add some unique JavaScript syntactical elements that don't exist in J. What that means is that that find methods recipe that we just ran for a Java code base and that we had originally written for JVM code bases actually works on JavaScript as well. You're just looking for different receiver types or different APIs, but a JavaScript method invocation is actually just a J method invocation. It's actually the same data fundamentally underneath the covers. If we move up one level to building in these programs, you imagine programs are just using the visitor pattern to go over these lossless semantic tree data structures, and we build on those the data flow and taint flow analysis algorithms that we're all familiar with. Interestingly, the exit points of those algorithms all overlap with the shared LST data model elements for the C family languages. So the same taint analysis algorithms written originally for Java function on JavaScript, function on Python, function on C#, function on Ruby, believe it or not. And this is a really interesting, kind of like there's an element of cross-language reuse we get out of building up these, higher and higher units of function on top of the LST. I think the way in which we get to that step 5, this flow across files in different repositories, which as far as I know was this inter-repository taint analysis capability has eluded the AppSec community, I think, pretty much to this point, right? The way we really do this is by identifying, you can see there's going to be multiple components to this. I'm going to first identify this particular literal assigned to a field, and then the question is whether that ultimately flows to some sink, right? It's just that sink might be in a different repository. So by building essentially a two-step or a two-phase approach here, whereby an analysis identifies sources, marks them in a data table, and then uses that data table as input to a subsequent recipe run, that allows us to basically pick up sources we identified in one run of a particular recipe and use them to see if we can find those sources flowing to sinks in that second phase. So it's the interaction really between being able to extract information out of the LST, record them in a data table, and then just feeding this into this tabular data that gets inputted back into another run of the same recipe that leads to inter-repository data flow analysis. Many of these patterns actually, we found, require multi-stage taint analyses as well, which is I think, an even more subtle challenge. If I'm looking at some class like A here, I could have fields that, like this algo AES, a key, something like that. And what I'm actually really looking for is whether one of these hard-coded literals goes through a multi-stage process that eventually leads to some data being encrypted. This is actually multiple independent taint analyses that are basically assembled into a pipeline, a state that you need to go from stage 1 to 2 to 3 all the way to 6 in order to see whether I truly have a problem or not. And so that's the abstraction we've built around Open Rewrite. You can assemble what's called a taint flow pipeline that has multiple stages. Each stage is what we would normally consider an individual taint spec in sort of like classical terms. And together, we could kind of see whether that flows to the concluding step 6 here. That same process I described earlier, where we run some sort of analysis and emit a data table, applies here as well. I'm just emitting a data table now with multiple stages in it, stage 1, 2, 3, 4, 5, 6. And for every run of a recipe, I'm taking every occurrence that I found that reached stage 1 and seeing if I can see it flow to stage 2. If there's any change in the data table, I just run again, and run again, and run again, and run again, until there's no change at all anymore at the end of the day. And that's really the technique that would enable this inter-repository taint flow pipelines of multiple stages. One of the challenges here is that at the point when I'm at stage 1, it's actually not clear to me yet whether it's of a particular taint type. So I think in classic taint analysis, we often, the identification of a source often returns a Boolean kind of yes or no. If I'm looking at this field data here, which is just an array of 16 bytes, I don't actually know yet when I first see this field if it could eventually be key material or if it could be an IV much later on. In fact, this field may be defined in one repository, and I don't see it used until some other repository much later. So when we define taint flow specs in this kind of world where we need inter-repository data flow analysis, we actually need to expand on the initial definition of how we define a taint flow spec to not just be, Boolean yes or no, whether a particular piece of code matches a source, but what are the potential taint types that this would emit? And then the next stage in the pipeline would say, I'm looking for sources that emitted particular taint types, and then seeing whether I can basically proceed to the next step. So it was really at the point when we went to this multi-stage taint flow pipeline that it became apparent that most of the libraries we have for taint analysis right now that return Booleans are really insufficient to the problem of identifying potential taint types that are not apparent in the code in which they're defined. Similarly, I think when we're looking at code, we're often interacting with binary dependencies. Binary dependencies we may not have the code for. Historically, obviously CodeQLs provide method summaries just with basic information about whether arguments flow to the return, or there's different kinds of analysis of this sort. Method summaries themselves are something that can be computed in advance and emitted in the form of those data tables, those rows and columns of information, and shoved in as inputs to a recipe that's running, such that when a recipe encounters a method call that's coming from a binary dependency, it's able to look up that, that summary or analysis from one of these pre-computed method summary tables to determine whether there's a problem or not. That's kind of the main concept I wanted to convey, and I'm not sure if this makes any sense, to be honest. This is kind of outside my realm usually. We tend to do application modernization stuff and kind of got dragged into this. Would welcome questions or thoughts on this at this point. Thanks.
Thank you. Great talk. I have a question. I came in a little bit late, so maybe you talked about it at the beginning. What is the need for the cross-repository analysis? Does that actually happen?
It does quite a bit, actually. It's things like this. It's like, you would have a core library that's setting some algorithm somewhere in some literal, and that core library gets used, it's like binary integration, inner source library gets used across many different repositories. Historically, if I think about a CodeQL method summary analysis, usually they provide method summary databases of a bunch of open source stuff. What you're missing then is everything that's, inside the kind of walls of my environment. It's a bit surprising just how much code, especially, I think especially our banking customers have. One of our early Canadian banking customers has about 500 million lines of code that we manage right now. That number is just mind-boggling, right? Like I don't know how to think about 500 million lines as in like any physical term. So I tried to do this little exercise where I thought if I just printed out the lines of code, that 500 million lines of code in books, and then stacked the books end to end, how long would the bookcase be, right? So if I'm standing here, what would your intuition be about where the bookcase ends?
Well, the length of this room?
Yeah, the length of this, that's what I would say. It would stretch all the way from Montreal to Miami, where I live. It's really staggering. That code base is 1/10 the size of one of our other banking customers, which in turn is 1/8 the size of the largest one we work with. So it's 80 trips between Montreal and Miami. This is, it's really, that's why these recipes, which are programs which are operating on, this kind of data, is important to be able to extract information out of that volume of code. If I just took the same text and like threw it all at a large language model, right, and said like, does this or does this not, you can imagine the cost of such a thing. So yeah, pretty interesting.
So is this cross-repo connection specific for crypto? Because like in traditional...
Specific for what, sorry?
For cryptography. For usage of the crypto primitives, is that use case common to have a separate library that has all your crypto primitives, and that's why you want to do that? For traditional security static analysis, when we talk about tainted data, it usually doesn't go across repos. It's rare. Right. Yeah.
Again, this is not really my area of expertise. I don't do a lot of this type of work. So I was a bit shocked at I don't think I was too surprised to hear inter-repository data flow or taint analysis being a requirement for this particular problem. This was the surprise to me, the sort of multi-stage problem, which is actually like another layer there where like it's not just an individual source and sink. It's individual source that may be more than one taint type, and whether that picks up again later when it's seen by potentially a different file or a different repository. So I would be surprised that the same inter-repository taint analysis wouldn't be useful for a SQL injection or something like that more classically, but yeah. Yes, sir.
I have a question. I mean, what you're doing here is very, very good at finding a lot of security issues, but how does this pertain specifically to post-quantum computing as opposed to regular finding secrets?
In some ways it isn't. It's interesting, right? Because it has nothing to do with what the technology actually looks like, right? Except for that the fear is that a particularly hard-coded algorithm will be insufficiently crypto-secure with a, so it's kind of like I have no idea how quantum works or anything really related to that. And another interesting dynamic is really, suppose I have it hard-coded right now, what should it be instead? Right. So identification is step one. Obviously, replacement of it with something else is step two. And there's this interesting dynamic where, what are we going to replace it with? We see IBM and others offering basically dynamic configuration offerings where, I'll replace your literal value with, something that's sourced at runtime. And I can see why they would want to be attached to that problem, because this is like ultimate vendor lock-in, right? That kind of thing. Of course, all our partner banks don't want this situation, right? Individually, they may not decide to build their own dynamic configuration, like algorithm injection mechanism. Together, they might, and that's, I think, first step, they really need to feel confident that they've identified the blast radius, and then I'll be interested to see whether they collaborate sufficiently on the replacement.
Well, the funny thing is you won't need to replace all the encryption. I mean,
that's right.
Strong symmetric encryption.
Exactly. That's right. Yeah. yeah, insufficiently strong is the problem. Yeah.
Yeah. Follow-up question around
Yes.
that. Can you talk a little bit more about with how the code is being refactored to be safe? Are these mostly in-place changes, for example, replacing one algorithm, RSA
Exactly.
248 with something post-quantum that is hardened? Or are these changes more large-scale to integrate, for example, a standardized library? How do your customers think about that?
Both, I think. Absolutely both. Because it's through a standardized library that obviously you wouldn't have to have this problem of going and changing it in a bunch of different places at a much later time. So our core technology really, and like I said, I didn't really start in this space. What we work on more often is something like move to Java 25 or Spring Boot something or whatever, that kind of thing. And so the mechanism would be like, this is a composite recipe consisting of hundreds of different things, but it's actually going to prepare the code change. That's whatever's required. And it's good to have this ability to make like large-scale change like this in a predictable manner. But even provided this tool, there's a distribution problem, like a social distribution problem. If I just take this now and I mass issue PRs to 100,000 repositories, like from a central team, the individual product teams are going to be reticent to merge that, right? It's pure risk when they receive it. I like to say PRs coming from external teams are like unwelcome advice coming from an in-law. You're just looking for a reason to reject it, right? So a lot of technologies I think we see emerging right now that focus a lot on PRs are not mature in the social engineering aspect of how to actually affect change at scale. So I think if I want to avoid having to go through this exercise of, promulgating this change every time I want to change the algorithm, then centralizing it to some internal library would certainly be helpful.
Cool. Thank you.
And I think you could do the same thing, replace a literal with a library call, essentially.
Yeah. And you almost went to answer this, my second question. How do you de-risk the changes you're making? Because obviously, as you said, if you just create a pull request, nobody is going to accept that, because how do I know it's still working?
Absolutely.
Especially if you do that across hundreds of millions of lines of code across many repositories. So how do you do that?
Yeah, when we look at recipes themselves, so I'll go to a transformational one that's a little more interesting, maybe even a JavaScript recipe here. Generally, the recipe itself will have a strong set of unit tests that basically do this kind of before after. Like, this is the code. This one we were looking for util.isArray, which is gone now in node 24. I need to replace it with array.isArray, or I need to replace this with a type guard or whatever. And so the unit test will have the before code and after code. There's a lot of verification built into this unit test, whether the format is preserved, whether the types are still resolvable at the end of the recipe, whether there's just kind of a lot of stuff that's baked into that. And so just like any software, when people write recipes, they write unit tests for all the scenarios that they can think of. Then you start somewhere, running it on some product team, find that you didn't think of this case, in this case, in this case, wind up adding more unit tests. And so it kind of progressively becomes more and more safe. And at some point, you kind of massively campaign on it. So it is always a progressive rollout. The bigger recipes, and they get huge. I mean, the big ones, like this is a migrate to Spring Boot 3.4. It's like 3,000 steps now. And basically, this is what we're asking developers to be aware of. Like, here's all the 3,000 different types of things that could change when you move from one thing to another. And, what's the problem? Why haven't you updated your 1,000 applications, right? Yeah.
Thank you.
Sure thing. Really great questions. Appreciate the discussion. What else do you have?
So forgive me again, I also missed the beginning of your talk.
Sure.
Flipping things around, say, starting with I care about compliance because
right.
someone has said I need to be PQC ready, and I don't know what that means, but I'm just going after, simple naive searching for where am I implementing anything that's cryptographically relevant.
Right.
And then doing this. Is there an intermediate step between grep and do the full source code cross-library analysis that we should be focusing on to sort of have a ramp?
I thought so. I think that's the way a lot of these teams started in these banks as well. They started with grep type tools. They moved to CodeQL type things. They moved to semgrep type things, right? And it's tough because I think at the scale, like we mentioned earlier, like 500 million lines to 5 billion lines of code, at that scale, false positives are just killer, right? It makes it inactionable. So it's, I don't know that there really, at their scale, I don't think that there really is, unfortunately, an intermediate step that's useful. And I think this is what actually keeps them up quite a bit at night. If you're one of those key executive there right now, this is really one of those, like, maybe a sufficiently powerful quantum chip never arrives. But if it does, it's a big problem.
So I think I've heard about the hybrid approaches that people are trying to do.
Yeah.
It's not like you can just cut it off from one thing to another. So your implementation, I think it makes sense to do hybrid.
When you say hybrid of which?
Hybrid at the, so you try to build slowly build compensating controls as you try to replace. So you use the classic security controls to mitigate some of the issues while you try to replace your PQC, the current cryptography with PQC.
Right. Not sure if it's a question, but I could imagine there's going to be some rollout sort of hybridization going on there. Yeah.
Yeah, it's more, it's a comment / question. Have you coded anything like that?
I think I can't really speak much to the rollout plan so much because frankly, like a lot of folks we work with are not super forthcoming about what their operational plans are for this kind of thing. We tend to get patterns that they're looking for that previously didn't really have the ability to find without substantial false positives. And so I think we're just kind of like narrowly directed at a particular part of the problem from their perspective. Yeah, so how computationally intensive? That's what's interesting. This loss of semantic tree data that we were showing earlier, like I mentioned, is like I could be looking at a method and there's millions of vertices hanging off of that. There's obviously going to be a lot of duplication there. So you have two calls to the same method that really points to the same type attribution information, which then suggests that we could actually have the same reference in memory. And so there's, in Open Rewrite, we do have, a referential deduplication on the type attribution level. For when we're operating on large code bases, what we do is take those Open Rewrite LSTs and serialize them to artifacts on disk, and then produce those artifacts for basically in batch for hundreds of millions or billions of lines of code. The most computationally expensive part of the operation is producing the LST in the first place, because it essentially requires clean compilation of the code base. You have to have all the dependencies, you have to have and associate them with the source sets that they belong to, and then we exercise the compiler programmatically and like walk it through its first few steps and then suck all the information out of it and put it over here. If that can be done basically offline and then serialized to disk, then you essentially have what amounts to a data warehouse or data lake of all that code, and the recipe comparatively is pretty quick running over that data. And so that really is the operating model that we try to pursue.
So you do the analysis, large application by large application. It's not like you go to a company and they point you to, here's our thousands of repositories.
No, that's exactly what they do, yeah. They'll point it at all of them, yeah, thousands.
Build every single.
That's right. That's right. And so actually part of the challenge in producing an LST for a wide variety of, just take Java alone, I could be encountering an enterprise repository that has Maven requires Java 8, or Gradle requires 21, or this requires, or both, or, you know, and so over time we've built up hundreds of these detectors that look at code on disk and say, this is the build tool, this is the version that it requires, here's where I find this on disk, and then kind of like side injectors. I think this is why we don't see a lot of LST type data out there, because this is kind of a brutal slog through every variation of build tool and version out there in the world. But it's also the big, I think there's a big chasm in capability between something in the AST that, you know, are kind of conventional SAS scanners and so forth used, and what's available here. So it's worth it if we get there. Yes.
So first, you're breaking my SBOM apart.
Yeah, you know, it's interesting you mentioned that. Really, the LST, you know, I mentioned markers earlier. Markers are just arbitrary data elements that hold just other information on them that's, you know, potentially unrelated to types or anything. So like if I was going to say, like, I'm looking for every version of Jackson in use here, regardless of whether it's direct or transitive, I'll be seeing the, like this particular dependency mock server netty in the code, but transitively this drags in Jackson core 214, et cetera, et cetera, et cetera. So there's a marker that's hanging, just a piece of data hanging on the top of this Groovy file, the Groovy LST, which represents the fully resolved transitive closure. In the case of like a Maven POM, we'll have the whole parent ancestry, the profiles that were activated at the time, all the dependency manager sections, the plugins that were activated, all their versions. And so you can do these kind of simulations of what if I change this, what happens, you know, the kind of thing. In many ways, the LST is really kind of a super, super, super SBOM, not just about dependencies, but everything in the text of the code plus everything the compiler knows about that code as well.
The question that I wanted to ask, other than just opening SBOM because I have to, is spend a lot of time with a small group of hackers that are starting to panic about the 2038 Unix EPUB. Is this going to be what we're going to have to do anyway for our entire code base before 2038? Is there a way, like, I'm hearing that simple library analysis, simple dependency analysis isn't going to be good enough.
It's not good enough, yeah. 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 Yeah.
That just means
It's super interesting.
organizations right now care about PQC,
Right.
whereas 2038 is going to break everything.
It's going to break a lot of things, yeah. Yeah. I think what's interesting about these recipes, and it took us a long time to get to this, but if I'm looking at the loss of semantic tree for a repository, a recipe can work in what we call a scanning recipe. It's multiple phases. There's a scanning phase where the recipe gets to see every LST once, essentially, and accumulate information to some accumulator. And then we do a second pass, which is the edit phase, where it has the opportunity to emit data or make changes or whatever the case might be. So oftentimes you have these interactions between, I see Jackson use here, and I also want to then maybe see if there's a code use that looks a certain way before I act on something. And so it's really being able to correlate those two things that are really, really important in many cases. Yeah. Yeah, I think we're at time, and so I'm happy to talk more, but I really appreciate the questions. It's made it much more interesting. Thank you.